Welcome to this presentation on causality and realizability. We will show that for sample systems, if we forbid unstable pole zero cancellation, if we can get a causal controller. We will also explain how to specify the delay to get implementable controller. We cannot realize this controller where Z inverse appears in the denominator. How do you see this? Just simplify this, it becomes Z plus 1 because you have Z, it is not implementable. All sample systems have at least one delay. This was discussed in one of the earlier videos. So I will write the transfer function of a sample system in this manner with Z power minus k, where k is greater or equal to 1. That is, G has at least one delay, and of course we assume that B naught is not equal to 0. Now suppose controller is not realizable, then we will have at least one Z power minus 1 in the denominator. Then there will be a cancellation between this Z minus 1 and one Z minus 1 here. Okay, there is a common factor Z inverse between the plant and the controller, and that common factor is given by Z minus 1 equals 0, or that is equivalent to having a pole at infinity, that is an unstable pole. So if we forbid unstable pole zero cancellation, then we would not have had a Z power minus 1, because there is definitely one Z to the power minus 1 because it is a sample system. If this cancellation is forbidden, Z inverse cannot appear in the denominator of the controller, and hence the controller becomes realizable. Now we will show that the closed loop delay has to be greater or equal to open loop delay. Let us take our transfer function g of z in our standard form, z power minus k into b by a, write it as polynomials in z inverse both in the numerator and in the denominator, and suppose b naught is not equal to 0. Now if we use a feedback controller of the form given here, where it is written once again in powers of z inverse in the numerator and in denominator with s naught not equal to 0, and d, the delay, greater or equal to 0. Remember, this is the controller that we are implementing. We cannot choose this d to be negative, because if we choose d to be negative, because we have the minus sign, you will have positive powers of z, which will result in prediction because of this non-zero term s naught. Let me write down the closed loop transfer function which is given here, and let me simplify it after substituting for g and gc. You can verify that it is equal to the expression given here. Let me start with this, and remember that d has to be greater or equal to 0. So the closed loop delay is given by k plus d, which is greater or equal to k, and which is nothing but the open loop delay. We can make this k plus d less than k only by choosing this d less than 0, but this will make the controller unrealizable. What happens if we go ahead and specify a wrong delay? We start with the plant of this type, which has 2 sample delay here, which is indicated by z to the power minus 2. We specify our overall transfer function capital T to have only one delay, so we have z to the power minus 1. So what is the expression for this capital T? It is ggc by 1 plus ggc. Suppose we back calculate from this the expression for gc. It is easy to verify this. I would suggest that you do this, and let us substitute for T and G from these two into this expression. we get the expression for GC. You get the expression of this type. I would want you to substitute and verify that you indeed get this expression, and this is unrealizable because you have 1 over z minus 1, which will be z to the power 1 in the numerator. This controller becomes unrealizable no matter what A is. Notice that there is some freedom in this A. What we are saying now is, it does not matter whatever A you choose, this controller is not implementable because of z to the power 1 that comes in the numerator here. With this, we have come to the end of this presentation. Thanks for joining.